Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to go through section 8.1, which has to deal with arc length. So we're going to talk about how to find the length of a curve, either defined as f of x or f of y. It actually won't matter. It'll basically be the exact same formula. However, first to do so, what we're going to think about is how we would partition some sort of a curve in order to come up with the formula for an arc length. So I'll get to this calculation in a moment. However, we're going to think about how we would split this up. And what we're also going to keep in mind for when we get to the calculations is the mean value theorem for derivatives, which I have written out here. If I have a planar curve, so say I have a curve like this, well, if I want to find the length of that, what I'm going to do is split it up into pieces. Maybe I split it up into there, 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 and there. So I split it up into 1, 2, 3, 4, 5, 6 partitions using 1, 2, 3, 4, 5, 6, 7 slices. Now, if I want to find the length of any one of those slices, what I'm going to do is take the first point up to the second point, and in order to find that length, I would start to approximate that by thinking of this as a right triangle. When I think about this as a right triangle, then I can find that length. If I draw that in red, I can find that length by using the Pythagorean theorem on that small triangle. The same would apply for the next partition, where I'd make another right triangle here, and I'd find an approximate value for the length using the Pythagorean theorem. Note that every time I do this, I'm not necessarily going to get to a really good answer, but I am going to get to an approximate answer. And I can get closer and closer the more I partition this. So with the current state of things, I would find each of those partitions using these right triangles. That are just defined by using the x and y coordinates. And that does pretty well. But the more and more I split this up, the more and more I split this up into a curve that's split up into a lot of these partitions, then that means the error that I have in between each partition is less and less. So I get better and better. So in order to find these, if I zoom in on one of them, for example, say I take this partition here and I zoom in on it, what I'm doing is I have this curve defined from this point to this point, and I think of a right triangle defined there to find this hypotenuse in red. Well, from this point to this point, the bottom leg would be defined by the change in x, and the vertical leg would be defined in the change in y. And that means the square root here, or the hypotenuse, would be defined as the square root of the change in x squared plus the change in y squared by using the Pythagorean theorem. And that's what I would be doing for each partition. That is what is explained down here with the equation. We have that the length you can define as the limit of these partitions, where you start to split up these partitions and make them smaller and smaller, or you just make more and more partitions. This p sub I minus 1 up to p sub I, this is the absolute length from one partition to the next. And we'd find that length, as I showed, by finding the square root of the change in x squared plus the change in y squared. Well, from the mean value theorem for derivatives, we can change the delta y, or the change in y, into f prime delta x, so we get this expression right there. And then because we see delta x squared in both of these terms, we can factor that out and then pull it out of the square root and just have delta x sitting outside the square root. And now that we see the limit of this sum with a delta x, that gives us our integral that we need, and we have the integral from a to b, or whatever, from point A to point B, whatever partition we're going on, of this integral of square root of 1 plus f prime x squared. And the same would apply if you're doing the same thing with y. And what I have here is equivalent to. So you can do this length for x by doing the square root of 1 plus f prime of x, so the function defined with x squared. Or if you want to do this with the change in y, so from c to d, you can do that as well with the square root of 1 plus f prime of y squared. So either way, it would be the same. So those are going to be the formulas that we use. These two on the bottom here are going to be our formulas for this section for the arc length of a curve. Note that this is for functions that are defined as x or y. However, you can also do this for parametric functions, functions that are defined as time progresses. And you may have done some parametric functions back in 1050, 1060, and probably Calc 1. And we'll get to the evaluation of this later on. We'll come back to this in Chapter 10. But I have out here outlined how you would do that same situation just with parametric. You would still end up with delta x, delta y, the change in both x and y, but delta x and delta y you're both going to define in parametric terms as f prime t and g prime t. You substitute those in, you could take out delta t squared out of the square root, and you instead get the length of the square root of f prime t squared plus g prime t squared. So this is going to be our parametric equation. Again, you won't need this yet. You'll see this in Chapter 10, but it's good to start to think about how this will relate to parametric curves moving forward. Again, the only two that we're going to need right now, or at least at this juncture, are the two for just f of x and f of y. So let's do a couple examples of those. Let's find the length of the curves on the given region. So we have y equals natural log of cosine x from 0 to pi thirds. Well, in order to do this, if we think about the equation, since we have y equals x, what we're going to be working with is from a to b square root of 1 plus f prime of x squared dx. That's what we need for the length. So that means we need to find the derivative of y, or f of x, and square that. So if we have y as that means that y prime, or f of f prime x, is going to be the derivative of natural log cosine of x by the chain rule. We'll have 1 over cosine of x, that would be the derivative of natural log, but then by the chain rule we take the derivative of the inside as well, which is negative sine of x. So we get negative sine of x over cosine of x, and that's the same thing as negative tangent of x. And then if we square that, y prime squared is just going to be tangent squared x. The negative will drop because it'll be squared. So then we can evaluate the length then from a to b, in this case from 0 to pi thirds, as the square root of 1 plus tangent squared x dx. We recognize 1 plus tangent squared as secant squared x by the Pythagorean identity. So we get 0 to pi thirds. The squared on secant will cancel out with the square root. So we get just the integral of secant of x dx. And then the integral of secant of x is the natural log of secant x plus tangent x from 0 to pi thirds. Then if we plug in our bounds, we get the natural log of secant of pi thirds. Well, cosine of pi thirds is 1/2, so this would be 2. And then tangent of pi thirds, well, sine would be root 3 over 2. Cosine is 1 over 2. So that's sine over cosine would just be root 3. And then if we plug in 0, we get minus natural log. If we plug in 0, we get secant of 0, which is 1, plus tangent of 0, which is 0, and natural log of 1 is 0. We get an answer of natural log of 2 plus root 3. And that's it. Then we can drop the absolute value there. So natural log of 2 plus root 3. Okay. Not too shabby. Let's do another one. Okay, this one's going to be a little bit tricky just because there's going to be a nice sneaky way to maneuver things here. Okay, so like last time, we have our function, but this is defined with y's. We have from 1 to 2 for y. However, in order to find the arc length, yet again, we are going to need to find what the derivative of this function is. So let's find x prime. That's going to be y to the third. The 4 is going to move down and divide 8, so 4 over 8 will give me 2. This is the same as y to the negative 2 over 4. So that negative 2 is going to come down, so it'll make it a minus. The 2 and the 4 will cancel, so I'll have another 2 on the bottom. And then y to the negative second will become y to the negative third. And I'm actually going to keep it like this, instead of maneuvering the y to the negative third to the bottom. If I plug this into my length formula, from 1 to 2, square root of 1 plus, I'm going to need to take these terms and square them. So if I do that up here to save a little bit of room, I will get y cubed over 2 squared, which is going to be y to the 6 over 4. Y cubed over 2 times y to the negative cubed over 2. The y's will cancel, so I'll just get 1/2 times negative 1/2, which is 1/4, twice. So that's minus 1/2 overall. And then negative y cubed over 2 squared will give me plus y to the negative 6 over 4. So that's what I'm going to get as my length formula here. 1/2 square root of 1 plus everything I just got. dy, not dx. We note that we can combine 1 and negative 1/2 to make a positive 1/2. And what I'm going to do is I'm going to put that positive 1/2 right where the negative 1/2 is. So I'll have y to the 6 over 4 plus 1/2 plus y to the negative 6 over 4 dy. The reason I do that is because this expression on the inside of my root looks exactly like the expression I had earlier, the only difference being that sign right there. It's a plus instead of a minus. Likewise, what that means is that the sign on the inside here is going to be a plus. So this actually becomes 1/2 square root of y cubed over 2 plus y to the negative cubed over 2 quantity squared dy. So now we just have 1/2. The square and the root will cancel, so we just have y cubed over 2 plus y to the negative cubed over 2 dy. That integrates to become, the first one will become y to the 4th over 8. And then the next one will become minus y to the negative 2nd over 4 from 1 to 2. If we plug in those bounds, we get 2 to the 4th. That's 16 over 8. Otherwise known as 2. Minus y to the negative 2, or if I even want to rewrite this as 1 over 4y squared. 2 here will give me minus 1 over 16. Minus, if I plug in 1, I get 1/8 minus 1/4. All right, make these all over 16, I guess, to make it easier. 32 over 16 minus 1 over 16 minus 2 over 16 plus 4 over 16. So minus 3 plus 4, that's a plus 1 overall. So that's 33 over 16 overall. All right, so that one was a little bit tricky simply because when you found what x prime was and squared that, we then combine that and we see a similar expression, so that helps us defactor that back to almost what we started with. And what we even notice is that the end result of the integral right here looks almost identical to what we started with, just with the difference of the sign in the middle. Very nice and interesting problem there. Okay. Now, if it's the case that we don't actually have an ending point, we just want to find an equation for the length, that is fine. We simply just have to have a starting point, which we're going to design or we're going to set up as our lower bound of an integral. And then we're going to designate the numerator or the upper bound of the integral as either x or y, depending on what variable we're working on. Then we'll take the original expression and just replace everything with t instead, or some other variable to act as a placeholder. That way we're going to find the overall integral from some starting point up to some arbitrary point in the future. This equation could be more useful than constantly doing this integral multiple times for different values. So let's do this one here. We have y equals x to the 3/2, and we're going to do from x greater than or equal to 1, so we're going to use 1 as a starting point. So again, we need to know what the derivative is. So we need to know y prime. That will be 3/2 x to the 1/2, or as we're going to write it, 3/2 t to the 1/2. If we square that, y prime quantity squared, we'll put that over to the side actually. Y prime quantity squared, we get 3/2 squared, which is 9/4, and t to the 1/2 squared, which is just t. So then overall we have our length then as the integral from our starting point 1 up to x square root of 1 plus f prime of t squared, which we found to be 9/4 t, dt. That's a nice and easy one. We can just set that as a u substitution, setting u to be 1 plus 9/4 t, du to just be 9/4 dt. So we have this as 4/9 du equals dt, and we can rewrite this. So 4/9 square root of u du. If we plug in our bounds, if we plug in 1, we get 1 plus 9/4, which is 13/4. And then for x, we get 1 plus 9/4 x. this becomes 4/9 u to the 3/2, and that 3/2 will have a 2/3 out here. And then we have this going from 13/4 to 1 plus 9/4 x. So we have overall 4/9 times 2/3. That will give me 8/27. Then we have 1 plus 9/4 x to the quantity 3/2 minus 13/4 to the 3/2. And that would be my answer. That would be an equation of the length of this curve from 1 up to some point. Now, what that minus 13/4 to the 3/2 does, that's cutting out the first unit of length for the curve. So basically from 0 to 1. That's why it has that subtraction there. Okay. So that should cover that. Let's do another example, though, one that might be a little bit longer. This one we have x equals 1/3, y squared plus 2 to the 3/2. Again, we're going to have to find a derivative, and again, we see a 3/2, so that should be a pretty convenient one like it was last time. X prime is going to be 1/3, the 3/2 is going to come out. Y squared plus 2 to the 1/2, and by the chain rule, we take the derivative of the inside to get 2y. So overall, 3's cancel, 2's cancel. We have y squared plus 2 to the 1/2. And then if we square that, we get y squared times y squared plus 2, otherwise known as y to the 4th, plus 2y squared. Or, since we're going to replace this with t, we get this as t to the 4th plus 2t squared. And now we can define this length from 0 as my starting point up to y as the square root of 1 plus t to the 4th. I'm going to try to make my t's curvy so they're recognizable. Plus 2t to the 2nd power dt. This on the inside can actually factor out really nicely. T to the 4th plus 2t squared plus 1, that's going to be t squared plus 1 quantity squared. That d factors very nicely. dt. And so we get 0 to y t squared plus 1 dt. So that gives us 1/3 t cubed plus t integrated from 0 to y. The 0 is going to cancel everything out, so that's pretty irrelevant. We just get the equation of 1/3 y cubed plus y. That's going to be our final equation there. The equation for the length of the curve, anyway. Okay, so that's how you would find arc length. Relatively short video this time. Most of this is just introducing what the formula for arc length is, and then applying it is relatively direct. Note that sometimes, since it does have a square root of 1 plus something squared, you may have to apply something like a trig substitution if necessary, but most of these should be solvable even without that, as you've seen with the 4 examples I've shown here. I've been able to maneuver and manipulate everything without having to deal with any trig substitutions. But keep in mind that those can be very helpful to you. If you have any questions, feel free to put those in the comments below or ask your instructor directly. With that said, I hope you have a nice day.